Hey guys, and welcome back to this class. In this lecture, I'm going to introduce you to the course project. This lecture will introduce you to the data we're going to use, and it's going to tell a story. Where did this data come from? What are we trying to do with it? And what is its business value? I hope this project will help you take all the theory and all the code and put it into real-life use. It's important to be able to take real data, which could be in the form of an Excel spreadsheet, an SQL table, or just plain log files, and format them so they are suitable for consumption by your deep learning algorithm. If you're not used to doing that, then this project will definitely help you. So let's get to the problem. Suppose you are a data scientist at an e-commerce store. We want to be able to predict user actions on our website. This could have direct monetary impact because if you could, let's say, predict when people are going to bounce, you can show them a pop-up or a pop-under and prompt them to convert or do some action other than leaving your site. You might be able to see what attributes of your site are weak and could be improved. For example, look at where people are beginning checkout but not completing it. Once you've examined the causes of users not completing their checkout, you can improve your website. Another example is maybe your mobile experience is not very user-friendly, so people aren't buying when they visit your website on mobile. By examining your data, you might be able to see that you can predict very accurately that people aren't buying when they're on mobile, telling you that you should probably enhance the mobile version of your site. You always want to make data-driven decisions and use science to improve your user experience. Let's now look at the data. The data is in the form of a CSV, which I expect you to be familiar with by now. It's just a table where each element in a line is separated by a comma. The first line of the file is the header. It tells us what each column means. First we've got is mobile. This tells us whether or not the user is visiting your site on a mobile device. This is binary, of course. 0 for not mobile, 1 for mobile. The next column is N products viewed. This tells you the number of products a user has viewed during the session when they do the user action, which is the label. This is numerical data that consists of integers that are strictly greater than or equal to 0. We'll discuss how to handle that later. The next column is visit duration. This will tell us how long, in minutes, a user was on your site. This is also numerical data that is greater than or equal to 0, but they are not integers. The next column is returning visitor. This is another binary variable, 0 if the user is a new user, and 1 if the user is a returning user. The next column is time of day. Time is a number, but we're going to treat it as a category. Time is a different kind of number in general because it's cyclical. So 11 p.m. is 23 hours after the previous 12 a.m., but it's also 1 hour before the next 12 a.m. When we're working with geometrical distances like we do in machine learning, this difference matters. One simple way of treating this data is just to bucket them into categories. So we'll use the code 0 to mean 12 a.m. to 6 a.m., the code 1 to mean 6 a.m. to 12 p.m., the code 2 to mean 12 p.m. to 6 p.m., and the code 3 to mean 6 p.m. to 12 a.m. The assumption here is that users in the same bucket will behave similarly. The last column is label. We're going to have 4 labels: bounce, add to cart, begin checkout, and finish checkout. Bounce means the user just left your site. Add to cart means the user added to their cart but did not begin the checkout process. Begin checkout means they started the checkout process but never completed it. Finish checkout means they paid and you got a successful order. Clearly this is a classification problem, so we can use logistic regression and neural networks. In my logistic regression class, I'm only going to show you how to do binary classification, while in my deep learning class, I'm going to show you how to classify an arbitrary number of classes. I do that at the next level because the math is a little harder. This means that for the logistic regression class, we're going to ignore the last 2 classes and just try to train and predict on the data where the label is either bounce or add to cart. You can, of course, feel free to read ahead or build multiple binary classifiers, which I always encourage. Practice is good. Now let's talk about data processing. You of course can't feed categories into your logistic model or your neural network, because these things work on numerical vectors. You might already know this from my linear regression class, but just in case you don't, the solution is called one-hot encoding. This means that if we have 3 different categories, we'll use 3 different columns to represent them. We then just set the column that represents the category for each sample to 1. For example, we have our 4 time categories, 0, 1, 2, and 3. This means we'll have 4 columns. If the time bucket for my sample is 3, then I'll set the 4th column to 1. If the time bucket for my sample is 2, I'll set the 3rd column to 1, and so on. Of course, this means only one of these 4 columns will have a 1 for any sample. So that's what we'll do for the time column. Use one-hot encoding. What about isMobile and isReturningVisitor? Aren't those also categories? Yes, they are, and technically we could turn them into 2 columns, but we don't necessarily need to. Remember that each weight tells us the effect of that variable being on. If we had an off column, the weight for that dimension would tell us the effect of that variable being off. By not having an off column, we're basically absorbing the off effect into the bias term. Finally, let's talk about numerical columns, end product viewed and visitor duration. We know that both of these are numbers that have to be 0 or bigger. The fact that end product viewed is an integer means that technically we could treat it like a category, but it's more like a number on a scale, which itself has meaning. We know that 0 is closer to 1 than it is to 2. That has meaning. We would expect that 1.5 would have the meaning in between 1 and 2. For example, if all users who viewed 3 or fewer products didn't convert, and all users who viewed more than 3 products convert, then we would expect a user who has viewed 2.5 products to also not convert, or a user who has viewed 0.1 products not to convert. You wouldn't expect, based on the above rule, that a user who viewed 0.5 products to suddenly convert because 0.5 is some kind of special value. Therefore, scale and distance are important. One simple way to treat numbers is to normalize them first. That means subtracting the mean and dividing by the standard deviation. That makes it so the data is centered around 0 with a standard deviation of 1. Putting numbers in this small range means that functions like the sigmoid function will have a more pronounced effect on them. For example, sigmoid of 10 is approximately equal to sigmoid of 11, which is approximately equal to sigmoid of 12. That's not very useful, so we're going to normalize our data first. So how will this project be incorporated into the course? Well, each supervised machine learning model typically has 2 main tasks. The first is prediction. That's taking an input and trying to accurately compute the output. The second is training. How do you alter the weights of the model so that the model can accurately compute the output? You'll see that for each of these tasks, there is a corresponding section in this course. We first cover prediction, or in other words, how to get output from your model. So once you've learned all the theory for how to do that, we'll return to this e-commerce example, create a model, and attempt to make predictions from it. The next section will focus on the training. How can we train this model so that it actually makes accurate predictions? How accurate can we get? Once we've learned all the theory behind training, we'll return to this e-commerce example and train the model to see how accurate we can get it. Finally, where can you get all this code and data? If you make a mistake when you're coding along, or you just want to run the code and see what it does, check out github.com/lazyprogrammer/machine learning examples and look in the folder ANN Logistic Extra.